So, great. So, and hello to our home listeners. So here we go. So why do you care about computing? A brief history, a very short break, just enough to get a glass of water or a cigarette, and then how to work with computers and programming inspirational speech. So think of me as inspirational speech. And of course questions. So the question is, why computing? People have been doing computing for a gazillion years, you know, and it becomes essential in a whole bunch of things. We've got computing, science, philosophy. It turned out that a lot of modern philosophy actually comes from computing. And for those of you who think capitalism isn't that weird, we have commerce, which is, of course, a classic thing that now people use this. So what we have now is, we're going to go start from the dawn of time. Then we're going to go to the kind of what I call the steampunk era, which is the dawn of computing. I spent perhaps a little long on this because these machines are all extremely physically beautiful and have cool names. So I kind of indulged myself because, oh, it's so pretty, you got to look at this one. And then we're going to look at modern times. And, oh, damn, I skipped ahead one. I should add, the other thing I did is I kind of I spent more time on the hardware and I cheaped out on the software side. Even though I'm a software guy, the reason is the software side just isn't as interesting. So I'm going to give you some of the key points that you'll need to know about that, but that's probably going to be about 20% of this part of it. So here's a question for all of you. When was the first mechanical calculator invented? We're talking about we're looking at what the dawn of time is. So we'll start with this. Any idea? Any guesses? Just throw it down.
Consider the abacus.
Oh, but no, well, this is you're getting out of the game here, but this is a mechanical calculator, right? Abacus isn't really mechanical, it doesn't have gears and wires. The abacus is quite a bit before that. Well, yeah, I don't expect anybody to know this. And this is Blaise Pascal, this charming guy, very interested. He was like, and he was 19 years old when he invented this thing. It took him 3 years and 50 prototypes to come up with the first mechanical calculator. And this guy, he did all sorts of amazing things. Projective geometry, he started. Probability theory, one of the pioneers of this. Physics, he was one of the people who actually first disproved the whole idea that nature abhors a vacuum. Unfortunately, he caught a nasty religion when he was 31 years old. He started all work on science and mathematics and died 9 years later miserably. So we only got a tiny bit of work from him, and one of the things is the first mechanical calculator. But let's go the next, and this is it. It's the Blaise Pascal's Pascaline. And it's a beautiful little thing. I've always wanted to see the original thing, and would do calculations up to 6 digits, which seems no big deal now, but at the time, looking at hundreds of tiny gears he made by hand was an amazing thing. But that isn't really the dawn of time. Is this the dawn of time? Well, here we go. Here we have today, modern computers. That's when the US started, and that's the Pascaline. So you can see, this isn't really the dawn of time. So let's go back a bit more. And you said, when was the first calculating device invented? And as you said, it's the abacus. Anybody guesses to when the abacus? Hey, Steve. Guesses to when? 3,000 years ago?
I said 6,000.
Oh, 6,000. You're actually 6,000 closer than 3,000. It was actually 4,500 years ago. Well, that's pretty good. Actually, most people way underestimate this, how far it goes back. So, so the question is just, and the abacus is a beautiful, another really entertaining instrument. One of the nice things about the abacus was it was the state of the art for 3,000 years. Even in, when was this? 1946, November 12th, 1946, there was a competition between a trained abacus user and a desk calculator user actually run by the US Navy. And the abacus won, right? 3 out of 4 tries this. So, unfortunately, I call it the abacus's last hurrah. The usual articles call it the abacus proves its might, but that's kind of the end of the abacus. But still, that was pretty amazing. 3,000-year run at the apex of abacuses and the apex of calculating machines. Okay, so are we talking the dawn of time? So here we go. We can see now the Pascaline. That's a tiny thing. That's today. The year 1. There was no year 0. Software puts one in. There's no year 0. Sorry. And here's the abacus. Nobody's quite sure when it was invented, but sometime between 2800 and 2300. So is that really the dawn of time? No, we haven't hit the dawn of time yet. So when were objects first used to compute? I didn't even know this before a week ago, so I'm not even going to ask. It turns out they used these beautiful play tokens about 6,000 years ago. This is in fact a circular envelope for clay tokens, and these are the tokens themselves. Each token, can you see, Rachel? Great. Each token actually represented a specific possession that you had. So they'd have bull tokens, and I assume sheep tokens, and all these other tokens. Initially, they started off making very complicated tokens for each item. Very quickly, by about 6,000, about 4,000 BC, they'd scaled it all back because people were all very lazy, and they became stylized tiny beads that they put on a string to do calculations and keep track of things. So we're getting like 6,000 years ago. You can see, look, there's the abacus. So 6,000 years ago, is that the dawn of time? No, it turns out that isn't the dawn of time. When were objects first used to store numbers? Any guesses? Yeah, again, how would you know? But so the first thing to store a number was the tally stick. Tally stick where you cut notches in. And the first tally stick we have goes back 35,000 years. Yes, these beautiful, it doesn't come up so well. It's a shame this doesn't come up on the image, because this is a really beautiful image of these things, these bones that were discovered, very carefully notched. Each one has 29 notches exactly, which makes people think that they were either lunar calendars or menstrual calculators based on this. In this tiny country called Swaziland that's like not even five times the size of Long Island, and almost completely surrounded by South Africa. So this goes back 35,000 years. That's really what I think of the dawn of time. You can see basically we have all this stuff glues up in here, and we have the Lumbobo bones. And just to give you some perspective, because I wasn't 35,000 years doesn't mean much to me. So we have here, fire was discovered sometime about 400,000, between 400,000 and 120,000. This isn't really a calculation, but I wanted to know this, so you get to know it too. There's actual hard evidence for 120,000. Most scholars agree that it probably goes back to 400,000. There's some evidence that hominins, i.e. our British cousins, were using fire as long as 2 million years ago, but if I put that on the chart, it wouldn't be there. So you can see we've got fire, we've got the bone, and then there's the wheel. I put the wheel, and look how close the wheel is to today. So people have been calculating actually like many times longer than they've had the wheel, which is something I did not realize before I started this. All right, so we got to get back in history, and one of the key things that's happened is every time somebody comes up with a new mechanism to calculate, immediately people start using it and making things, whether for good and bad. Like about 5,000 years ago, people discovered that if you took a triangle with 3, 4, and 5 sides, you could get a right angle. So fast forward a few hundred years, you get the pyramids. Same technique. By the way, again, I discovered I was wrong. I don't know, perhaps you heard in school about the 3, 4, 5 thing, and they said, they would knot a rope. Well, some guy online tried to actually knot a rope this way to get equal divisions, and he said he was unable to do it after trying almost a dozen times. So, and I looked it up, and actually, even though I was taught that my whole childhood, they would knot a rope into 12 equal parts and glue it together, and that was a right angle. It seems it's actually impossible to do, and there's no records of it whatsoever. But they did know about the 3, 4, 5 triangle, so they're clearly using this to build this sort of thing. Or another thing is, again, about 3500 BC, they first came up with written numbers. Fast forward not even 200 years, and we came up with taxes, literally Hammurabi. And in fact, one of our earliest, humanity's earliest records of any systematic numbers at all are this amazing record-keeping thing of, Hammurabi and that era, where they have thousands of tax records. It's why they're able to really work out this language is completely dead, because they have these systematic records like, okay, these are clearly oxen, these are clearly goats, and this sort of thing is. So, all right, so we're going to jump back. There are many interesting parts I had to cut out. Partly because we don't have time, partly because I didn't know where to fit them in. And this is something I didn't know where to fit in, so I'm going to throw it in here because it actually goes back to antiquity. We're going to only talk about digital computers, computers that talk about numbers, that use numbers. But there's a whole other branch of computing called analog computers. Those are computers without numbers. They use continuous values, like dials that turn, water levels, they're water analog computers, electrical voltages. Well, those turn out to be very common. Pressure. And the reason I'm pointing this out, of course, is there were some ultra cool machines in ancient times that did these. I should add, you will never program an analog computer. I have seen one in a museum. That is as close as I've gotten. You'll probably see one in a museum if you care to, but you will never get to program one, which is probably just as well. It looks like a hassle. So the first one, this is called the Antikythera mechanism. I took this beautiful X-ray that somebody had of the whole thing. Basically, Jacques Cousteau, of all people, found about 1970 this what appeared to just be a rock, but he was a pretty smart guy. And there was a conch sticking out of it. So slowly, since I was a kid, it moved from unexplained mystery to well understood device. And it turned out that this was a primitive analog computer. Oh, sorry, it's from 1900, that's right. Jacques Cousteau was the first guy to figure out that it was actually, that there was mechanism in there. But this is actually from the 1st century before Common Era, what they used to call BC, but now they don't, it's all been, gotten rid of the, and who knows when Christ was born anyway, right? So, or if at all, whatever. So it was actually an astronomical calculator, extremely precise. People have subsequently made copies of it, and it would have worked well for like 100 years of predicting astrology. And it was, a lovely, tiny little thing that people made and must have been somebody's treasure for years until it was lost in a shipwreck about 2,000 years ago. And somebody says, in fact, I have a quote here that says, "This device is just extraordinary, the only thing of its kind. The design is beautiful, the astronomy is exactly right. The way the mechanics of design just makes your jaw drop. Whoever has done it has done it extremely carefully. In terms of historic and scarcity value, I have to regard this mechanism as being more valuable than the Mona Lisa." So, unfortunately, if you see the thing, it looks like a bunch of coral-encrusted parts. You couldn't see until they actually put it together, which was only about 20 years ago. They didn't know that it did anything exciting. Now, there's another one I just had to throw it in because it's really cool. It's called the South Pointing Chariot. It's from China. When was it? 3rd century China. Now, it's kind of a shame that this rather Jurassic technology never took off, because what this is it is a compass without magnets. They hadn't figured out the whole magnet compass thing. So instead, what they had was this chariot with these little gear computer mechanism that would constantly keep that little guy. This is actually a replica, by the way. There's no existing copies of one of these. But this little guy at the top, the pictures of this would always point south no matter how you move the chariot. And it's almost certain that they use something called differential gears. And those of you who know cars know that these are the things that allow your car to do things like shift gears and turn corners and all this sort of thing. They don't know for sure that they use differential gears, but most people, they had to, because there was no way to put this clever little thing together without using differential gears. So that's, and people only really figured this out fairly recently again. For a long time, they just thought it was, a lot of times people say, oh, it's a ritual item. And that's just the kind of shorthand for, oh, we have no idea what it is. So they figured this out, and again, it's another form of an analog computer. There's no actual numbers, but it is performing computation. South. All right, great. So, so now we have 2 more things. This is some of you may have heard these if you're World War II buffs. They're called the Norden and Sperry bomb sites, and these were pretty big for our guys, so to speak, in the Second World War, because they allowed you to actually aim a bomb automatically. And it's why are there 2 of these? Why are there 2 names? It's a desperately complex story of patents and intellectual property and all this stuff. You thought with a war they might have not been able to do it. No. Basically, Norden left Sperry, took a lot of their ideas, put other ideas in, lawsuits, right in the middle of the war, all this sort of thing. They both were producing them. Chaos. It's pretty clever because it actually figures out how to drop the bomb, not only based on the current conditions, but actually it was taking a linkage, what we call today data, from the autopilot. And literally this was all being done by just pure electrical levels. There wasn't any actual data. So it was a very clever device. You can see this is, it's the last, these 2 are the last great analog computers. Right? That was kind of it. After that, analog was only, but they were in use all the way from World War II, all the way up to Vietnam. So if you see people in Vietnam who are not on helicopters, of course, too big for those, but all those B-2 bombers, they had these Norden bomb sites, and there's a beautiful picture of these things. A bit small here, but they're like, if you see them, it's this massive mechanism. Everybody should have one. You can get them on eBay for like $10,000, so I'm not tempted. My wife would kill me. All right, so back to digital. Okay, so back to digital. From now on, we're never going to hear about analog computers again. I just had to tell you about them. All right, so back to digital here. So there was really almost no progress between the abacus, which is 3,500 years ago, and the 17th century. Basically, for what people were doing, the abacus was absolutely great. People loved it. It did its stuff. You could do added addition, multiplication, division. What else did you need? Now, there is one exception. Raymond Uy, thank you, who in the 13th century, very interesting guy. He actually proposed this thing called the ars combinatoria. What he had was a machine. There's no, unfortunately, visual record of this machine. It had multiple wheels that allowed you to make all combinations of facts. And he actually proposed what we would call today automated theorem proving, basically. The unfortunate part is that he used this entirely as a tool to convert Muslims to Christianity. And then later he broadened his thing to convert Jews and other people to Christianity. But so it's a little bit of a shame because he was kind of onto this good thing and then he used it to entirely sell this one thing. And probably many of you don't know this, but it's a beautiful children's book that I grew up with called The Box of Delights. This was the cover of the book I had when I was a kid. It's a great book where this kid falls asleep the night before Christmas and he's visited by Raymond Uy, who gives him this box, which is probably one of the machines that has all those dials. And there's also apparently a British made-for-TV movie of People Seem to Love, but I never found out about it. So if you have a kid and they like Christmas, fantastic book. Still, it's been in print for over 100 years.
Point of information, is this the same Masefield who was once poet laureate?
It is exactly the same John Masefield. Very good point. In fact, it's in, it's in my notes. So, right, a very good point is here. So suddenly things started to go along, and then suddenly things started to really hot up in the 1600s with John Napier. Now, John Napier was an absolute prodigy, and he invented two things which changed calculation for a really long time up on the modern era. The first one was that it was logarithms. Now, I had a section in here where I explained to you what logarithms were. I deleted it. They're absolutely fascinating, and what they do is they allow you to do multiplication by means of addition, or taking powers by multiplication. Logarithms before the modern computer was it. If you wanted to do scientific calculations, you did logarithms, or you stayed at home. And he basically came up with these on his own with very little influence, and it's no exaggeration to say that for over 300 years, the logarithm was the king of computation. Again, we won't be needing to do these now, we can just do everything exactly, but it was a big deal. And then he also came up with a much less known device called Napier's bones. Well, we don't have quite, I wish I had more resolution on this, but it's a beautiful little machine, again, with numerous little turning things that turn, and it lets you not only do addition, but multiplication. And strangely enough, as a child, they used to sell variations of these things made out of basically what I call tin, probably cheap steel. Only when I was researching this did I associate these bizarre childhood toys that let you do multiplication fast with Napier's bones. So this was, while this only was good for about 30 years, it was the first time somebody thought, we can do better than the abacus. So it was a big step for this, and Napier just, he was just very influential in a vast number of ways. He did physics, and like a lot of people, he was a real polymath. But the logarithm is the thing we use to this very day. So, and a bunch of other English people started to get involved. We have, and we ended up with the slide rule, which is basically, as I call it, logarithms on a stick. I'm not going to go through the mechanism of the slide rule there. We have three separate people. Gunther actually was the first one to put a logarithm on a stick, but he only had one stick. He actually created, and Gunther was a really cool guy. I wish I had time to go into it. Oh, I think I do have a picture of him coming up. No, too bad. He also created a whole bunch of things: the chain, the quadrant, the sector, the scale. Each of these is cool instruments to do with surveying, to do with measuring. And so he was quite a tinkerer. And plus, he was one of the first scientists to actually write his results in English. At the time, almost everybody wrote results in French. For example, at Wingate, who was the first guy to actually publish a description of how this would work, he published it all in French. Even though he was English, all these people in English, he published in French. And people actually criticized Gunther a lot for publishing in English. They're like, it's crass. But of course, today, he has the last laugh. It's almost, it's like, certainly a plurality of science papers are published in English. So for years, and we're talking, again, 300 years, it's a very long time, a slide rule was the emblem of science and engineering. The funny part is, in 50 science fiction novels, they'll be talking about engineers with great computers, and they'll have, in these science fiction novels, slide rules at their belts. They hadn't gotten, it's funny that they understood the great computers thing, but they just assumed everybody would have the slide rule. I got a slide rule when I was 11 years old, and it was my constant companion for a very long time, because it lets you get good on, it lets you do almost any calculation you like. So voila. So, and we get back to Blaise Pascal, I mentioned. 1642 and the first mechanical calculator, and again, that set up another 300 years of gradual improvements on these kind of pointless calculators. The one interesting part was this thing called Burroughs calculators, which started with the fantastic name of American Arithmometer Company. Arithmometer, I didn't even know this word existed. And the reason I'm mentioning this is they became scandalously wealthy. The original Burroughs people had a lot of kids, and Steve knows this one already, is one of those kids turned out to be William S. Burroughs. So if it wasn't for the Burroughs Calculator Company, you would not have Naked Lunch and a gazillion other disturbing classics of cut and paste. Not cut and paste. So basically so there's a sudden burst in the 17th century. Everybody's doing it. Many English people, everybody I mentioned was English there. For some reason, there's no real explanation. I just assume everybody's competing with each other, and then nothing. It just stops. And there's actually no changes. But there's one thing that people didn't realize at the time was a major step towards computation, and that was I say stagnation here. There's little. I'm behind my own notes. Very little progress for 3 centuries. Listen, mechanical calculators for finance, slide rules for science. Mechanical calculators do addition and some multiplication. Of course, your multiplication is done by repeated addition, but what do you want? And gets exact answers to the penny. Slide rules let you do calculations with huge magnitudes and do logarithms and things approximately to 4 or 5 decimal places, which is fine for science, not for commerce, if you don't want to be 20 cents off every time you make a mistake. Between these two, that was it. 300 years. However, there was a little glimmer, and it was this beautiful device, which, again, you can't quite see the loveliness, but I will be putting this up so you can see these, and I should put links in. It's called the Jacquard loom. What the Jacquard loom is basically a programmable loom in 1801, and it's programmed with punch cards. You can see here there's a whole belt full of punch cards to produce new patterns without having somebody actually tie each thing. If you see how looms worked for complex patterns before that, they either had simple patterns that were done by geometry in the loom, or somebody would tie each thing. There are techniques like a cat and other things, but it basically involves mainly women, unfortunately, tying hundreds of thousands of tiny knots, going blind and losing the use of their hands. So this was a huge advance. I hadn't realized till I did this. I thought, they were doing these simple block patterns because that's what I saw. But what I found out is this is the first digital photo. This guy was Jacquard. He actually he loomed, not printed, but loomed a photograph of himself on one of these Jacquard looms in 1839. Joseph Marie Jacquard, which used, get this, 24,000 punch cards to make that picture of him. So that was kind of his, clearly his show off and his calling card. But this made an impression on a lot of people, and this led actually, tangentially, to our next step. So, the big step that's coming is, of course, the programmable computer. What we have up until now is machines that let you make specific calculations. But if you want to make the same calculation over and over again, you have to keep doing it with the machine. And of course now, you all know the secret, but at the time, people only slowly came onto this fact. And there's one really seminal figure here. Oh, teaching. Yeah, again, what's the point of these notes if I just could read them off? So there's a seminal figure here, Charles Babbage. Now, some of you may have heard of him. He's a really interesting guy. I wish I could give a whole lecture on him. He was a real polymath. He did all these amazing things. He was also an incredible curmudgeon, like really grumpy guy. And one of the things, he had this lifelong vendetta against street musicians in London. He endless petitions, going to meetings about it. He hated for some reason, he just endlessly hated these people. And it's kind of astonishing while he was doing these great things, he was also obsessively harassing street musicians. So there we go. And he came up with two absolutely brilliant things. So brilliant that he wasn't able to construct them in his time. The first one was called the difference engine, 1822, and that was kind of, it was somewhere between a mechanical calculator and a programmable calculator. You could arrange it to do repetitive tasks, but it wasn't programmable in a way that you or I would understand. Now, this was never actually, and there's a famous book by science fiction readers, by Gibson and Sterling, called The Difference Engine. So it would have been a behemoth, this thing, absolutely huge, 25,000 parts, 15 tons. It would have been 8 feet tall. In fact, when I say would have, well, he was never able to build it. But in 1991, a museum in London, whose name escapes me because I didn't put it in my slides, actually set out to build this using only the technology he would have had in his day. So they set out to build this with Victorian tolerances and Victorian machinery, and 9 years later they actually completed building his difference engine, and they turned it on and it worked. It absolutely did exactly what he said, and this proves that he knew what he was doing. But the real advance he had was the analytic engine, and that was even more theoretical. Nobody's ever tried to build it. It would have been really, with mechanical parts, it would have been almost inconceivably difficult to build. The analytical engine was a fully programmable computer, and it seems very clear that his design would have worked. He was a very systematic guy. Now, and so this is just like you feel a bit bad for this guy, because like 100 years more before there's any possibility of doing this, he saw this and he never in his life actually had his hands on some computation. However, he had some consolations, and one of them is Ada Lovelace. Ada Lovelace she's another one of those great figures that you could do a whole lecture on. She was Byron's only legitimate daughter, although she never actually met Byron, who seems to me to be a bit of a prick from reading up on this sort of thing. And she suffered from numerous illnesses throughout her life, which sometimes left her bedridden and things, but the upside was she spent a great deal of time studying very non-feminine things. And one of those things was mathematics. And she was really one of the first great female mathematicians. She was actually quite a dilettante. She studied things that we consider kind of dodgy but okay today, like mesmerism, which has become hypnotism now, and also things we consider downright stupid, like phrenology, which is telling people's personalities by the bumps on their heads. You don't often see this, but you often see charts when they're trying to convince you it's old time. They'll show you a chart of the head with like bits all kind of, that's phrenology. So the main thing that's interesting about her is that she met Babbage when he was 42 and she was 18, when he was showing off a machine called Silver Dancer. There's no pictures of it. Sounds great though. And they met at a party and they instantly hit it off. As far as I know, there was never any impropriety, but they became fast friends for the rest of her life. And you see, the rest of her life, she died very young, unfortunately. But she became really entranced by this machine and continued to write and publicize this machine. Particularly, she's particularly well known for like 3 things involving this. The first one is that she was the first one to actually write a computer program. And it's pretty gutsy to write a computer program when the computer you were writing for wasn't to be built for more than 100. In fact, his computer was never built, but no computer you could have existed for more than 100 years. But she wrote this, and again, only in the last 20 years did she get kind of dredged up, and people initially, she's some chick. But then they actually worked, some hardworking grad student actually simulated her algorithm, and it worked. It was actually a working program, which is pretty impressive for this girl who was probably at the time 27 and only had a few years to live, unfortunately. So she also invented the first algorithm for actually something pretty obscure and mathematical called Bernoulli numbers, which I won't go into, except to say that I couldn't remember them from my youth, and I'll bet you nobody in the room's ever heard of them. And here's some young girl with no formal training and just talking to a lot of people, actually writing the first algorithm for something really non-trivial. But there's also two very interesting theoretical things that also came out not quite so recently, in the last 30 years from her writings. One of them is, she was the first person to understand that once you could do computations with numbers, you could do computations for things that weren't numeric. I mean, of course, now when you see computers that are like, you know, here I'm doing displays and graphics, it's obvious to you, but it wasn't obvious to anybody else. I'm sorry, I missed a totally cool point. I have to backtrack here. Charles Babbage, do you remember him? Do you remember that beautiful digital picture? He bought one when he was young. He bought one of those digital pictures. And he spent a long time thinking and writing about this, and his, I'm going to go back just one slide, his analytical engine, so he bought it between 1822 and 1837, and as a result, his analytical engine was going to use punch cards as its storage mechanism. So you can see that, while it was a very limited seed in 1801, the Jacqueline limit didn't fall on completely stony soil there. Sorry, I forgot that. So she actually said, I have a great quote from her. She said, supposing, for instance, that the fundamental notions relations of pitch sound in the science of harmony and of musical composition were susceptible of such expression and adaptations, the engine, that's the analytic engine, might compose elaborate and scientific pieces of music of any degree of complexity or extent. So, and she talked about this with other things. That's the clearest thing where she really points out she understood that you could do anything you liked, not just numbers. Also, I discovered this recently, she was the first person to suggest maybe we could create a mathematical model of the brain and nerves. She actually wrote about this, and she was completely wrong about the details, but how was she going to know? She had no way to know that nothing was up there. So she was really great. She was really, in some ways, a kind of tragic figure. She died very young of uterine infection, almost certainly exacerbated by the serious bloodletting that they did to her. And she said something to her husband on her deathbed, which caused him to leave and never see her again. So people suspect it was some affair she had. But it's a pretty tragic end to her life at 37, I think it was. I didn't write this there. However, I'm going to end with a beautiful quote. Oh, well, I don't know what other stuff I put on here. She met Babbage at 18, designed the first program. I said all of these things. So there's a beautiful quote by Babbage. I have to put it in there where he said, "Forget this world and all its troubles, and if possible, its multitudinous charlatans. Everything in short but the enchantress of numbers," which is her. So she's definitely worth a tip of the hat to. Do you have a question? No. Oh, you just made an actor. Rachel, can I trouble you for glass and water? Thanks. Oh, actually, no, you're right there. Thanks. All right, what are we on here? So we're going to take a tiny little distraction into the theory of computation. Again, I had a lot of slides here. I kind of want. This is something I particularly love. It deals with things like Gödel, undecidability theory. There are all these things that if I talk to you for 20 or 30 minutes, at the end you're like, wow. We're not going to do that now. Particularly, there was a real question came about, what does it mean to be computable? And this is quite a bit before they actually had computers, so but it came about for a bunch of reasons. Due to a bigger question, what does it mean, what does truth mean in mathematics? A lot of great mathematicians are trying to actually work out what truth means, and they actually got it in an interesting way. But at the time, all these people were desperately working to say, oh, what does computability mean? And four different people came up with four completely different solutions to this. Firstly, Gödel, very famous character in his own right, he did all sorts of things, and Herbrand, a French mathematician I don't really know, came up with these recursive functions. Now those are pretty easy. They're like some generalization, addition, multiplication. They're functions that operate on numbers. And then Turing, we'll talk a little bit more about, you've probably heard of, invented something called the Turing machine, which is this abstract machine. It has a tape. It walks along the tape. It has a state. It can read and write to the tape. Church created this unbelievably beautiful, although rather obscure thing called the lambda calculus, where he's like, well, let's take the recursive functions and just get rid of the numbers. They're boring. So we're only going to have functions that work on other functions or themselves. So that's it. It's just very navel-gazing, but it's another model of computation. And then there's something, I only included this word, it's minor, but I've loved the name my whole life, called the post-correspondence problem. And it has nothing to do with the mail. It's actually, the guy's name is Post. So it's really a problem. You can think of it as a problem of just putting together two-dimensional jigsaw puzzles. That's all it is. And that was yet another model for computation. So all these people were working on these models simultaneously. Everybody's going, I'm going to win. And then at a certain point, through the work of mainly Turing, but also to a lesser extent Gödel and Church, they ran this amazing thing, which is all four of those were the same. Exactly the same. Anything that any of them could do, any of the other ones could do. And it was kind of a big shock to everybody because they were kind of, nobody had been expecting this. So there's a thing which is still unproved, you couldn't really prove it, called the Church-Turing thesis. That's all there is. All these four things, that's computable. There is no other definition computable. And of course, it's really hard to prove or disprove this. You know what I mean? How would you prove or disprove this? You know, you don't know what isn't computable, but it stood up. Nobody's found anything you'd want to do that isn't in this category. And particularly, I want to just show you quick pictures of two of these people because they're just interesting figures on their own right. Kurt Gödel was Austrian mathematician, died in the 60s. He grew increasingly eccentric over his life, but was still managed to be mostly presentable. And he's probably best known to people, not for his work on computability, but this amazing work on what's called undecidability. It's a very cool book I recommend to everybody called Gödel, Escher, Bach. Perhaps some of you heard of it? It's this ridiculously convoluted book that mixes Lewis Carroll with Gödel's work, and it has plays and it has endless jokes. And my favorite one is this sentence, no verb, right? Which I always like. And you know, so things that talk about themselves. Recursion, self-reference. It's a book about self-reference. And Gödel figures prominently in this. If I had, again, there's a whole talk in there. And then there's of course, the tragic Alan Turing. Now, Turing is probably best known for his work during the Second World War. The Germans, at the end of the First World War, he created something called Scorbius's Enigma. And again, the resolution of this display, it's unfortunately not enough to see the beautiful intricacies of the thing where you would type your message and a whole complicated series of gears like a Chinese puzzle would work, and then you would print out like a typewriter, except the output was encrypted. And the encryption used this incredibly difficult mechanism that the Germans absolutely were sure that couldn't be broken. As far as they could see, it was impossible because there were like quadrillions of possibilities. So it just seemed absolutely impossible. But no, Turing invented what was one of the first practical computing devices called the bomb. It's kind of in the series, they call it the bomb not because it looked like a bomb or anything, but because he didn't want anybody to know what it did, so they call it a bomb. Most people don't know this, but the tank, tanks, that name was coined by Winston Churchill for the same reason. He wanted it, now you think tank, okay, crank, 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 but he just wanted a thing that had no meaning whatsoever, and a tank just sounded like could be anything. So that's how, and also the atomic pile. Again, when they talked about the atomic pile, it was during the Second World War, towards the end, and they wanted a code word that had no meaning whatsoever, so they picked something generic like pile. Now, one of the things, I just have to point this out here, although it's not so, I don't think it's too completely fascinating, but it's usually left out that Turing could not possibly have done this without actually three Polish cryptographers, Marian Reshevsky, Jerry Rzyński, and Henryk Zygalski. Practice their names. And these guys actually fled Poland literally with the Nazis at their heels. Literally, yeah, more or less literally with the Nazis at their heels. Came to England with all of this mathematical work that they'd done on this, and none of all of this breaking of the Enigma code, which was could well have been made the difference in England's dying in the war and not dying. None of this could have been done without these guys, and they got completely overshadowed by Turing. And part of the reason is this was like one of the wackiest things ever. Basically, they knew the Germans had this thing, and the British were very big on creativity. They just got together all of the crazy people they could. They got together crossword puzzle experts. They got together people who like mathematical puzzles, actual mathematicians, linguists, people who studied dead languages, and they just put them in a room and said, solve this problem. There's a great anecdote, it's not even on my slides, but Turing was not somebody who was a patient man. And he sent a letter partway through the war to Churchill. And he said, there's like one line of politeness. Dear Mr. Churchill, I met you last year at such and such, such and such. We need 6 secretaries. We need 30 desks, blah, blah, blah. A tiny amount of stuff, actually. And you know, it's unconscionable the war effort is being held up by this tiny amount of resources. So Churchill gets this letter, he literally whips it open, looks it for 30 seconds, somebody happened to be there, scribbled something on it, handed it off to somebody, and he just scribbled it upon, give this man everything he wants. That was an instant decision, and again, led to potentially winning the war. So they worked desperately on this thing, and they had some advantages. The Germans got lazy. Sometimes they actually managed to capture undeciphered, both deciphered and undeciphered text. So that helped. The Germans knew that this might happen, though. It should have been impossible, but they didn't understand somebody would actually build a huge machine with thousands of rotating gears to actually do this. Not a general purpose machine. The funny part was that now we're getting this stuff that's a bit speculation. The bombing of Coventry was a big deal in England. It was very destructive. Coventry Cathedral, this beautiful cathedral, was completely destroyed. Tens of thousands of people lost their lives. Now there's some evidence that Churchill knew or had an idea this was happening and did not change anything because he felt that the intelligence that they'd gotten from being able to crack the German code was so important that it was worth taking this hit not to reveal that they had the ability to crack the German code. Now, it turned out after the war, when they captured all the German records, that the Germans had captured deciphered text from this machine. So, so what had happened? So it should have been curtains to the whole enterprise. But so the Germans went to their experts and said, well, we found these deciphered texts. What's here? And the experts were, well, it's impossible for this machine to be broken. No. So the Germans went and literally tortured a lot of people who had access to that cable. Very unfairly for them, but it worked out for us, the good guys. The Germans literally could not believe, even with the evidence in front of their eyes, that somebody could have broken this code. So it worked out very well. Unfortunately, I didn't come up with a slide for this next one. Unfortunately, after the war, things went a bit bad for Turing. He kind of burned out from doing this. He announced a great discovery, and then he was about to give a lecture, and he recanted and never told anybody what it was. But worse, he got arrested for homosexual behavior, which is really a bad scene. He kind of forced him to get arrested. The story is a bit sad. He liked rough trade and sort of younger guys. One of these younger rough guys stole his stereo system. So he went into the police station and complained. And the police asked, well, what's this guy's relationship to you? And he said what was described in the records as a vulgar description of their relationship. And then the policeman said basically something along the lines of, now, are you sure you want this to go on the record that way? And might have even advised him not to do it. It wasn't like they entrapped him. He actually was, the policeman definitely warned him and said, now you surely want to see the record. So it was put on the record that he had gay sex with this, not that young, but pretty young, like 17. Even today that might have been considered a bit askance. So, the treatment was particularly brutal. They gave this poor guy, it was good to see a picture of him at least. They gave this poor guy, Alan Turing, hormone treatments. He started to grow breasts. It was ridiculous. It was very, very cruel. And he proceeded in this very mythic fashion to put cyanide on an apple and ate it, a poisoned apple. People wondered why he did this. A lot of people, like myself and a bunch of others, suspected he was very close to his mother and he wanted to give his mother plausible deniability that he hadn't committed suicide. And indeed, she never believed he did. To the end of her days, she believed it was a lab accident. Interestingly enough, in the last few years, some evidence has come about that it could have been a lab accident because earlier on, when he was in happier days, He came very close to drinking cyanide by mistake in the lab because he was very, very sloppy with his. So he actually picked up something that had cyanide, and somebody says, like, no, don't drink that, you'll die. So it's conceivable that the poison apple. No, he almost certainly killed himself, and it's very sad. Just 2 years ago, or I guess about 4 years ago, Gordon Brown, at the time the Prime Minister of England, personally wrote an apology to Alan Turing, which I didn't include. You can look it up also because it would probably make me cry. It was really beautiful, and he was really like, you know, we're really sorry, we failed you, you did so much for us, and we failed you and a lot of other people. So it was a big apology, 40 years too late. So he's, you know, a beautiful and tragic figure in this whole field. All right, we're back to Turing's bomb. So now we're getting to the heart where we're actually getting to things that may be like stuff you're going to use. The first programmable computer, and this turns out to be done by somebody I had never heard of before I started this. His name is Konrad Zuse. Konrad Zuse, a very interesting and charming guy. Probably he wasn't so well known because, if you notice, he's a German guy in 1941. Near as I can tell, he wasn't. While he was a member of the Nazi Party, as everybody was, he seemed to be completely apolitical, just interested in his machines, and actually kind of like an idealistic guy. So, what to say, but it's probably why he's not well known. And this guy has a huge record of achievement on his background. He's not only invented the first programmable computer, the Z3, he's also the first commercial computer, the first computer company, the first high-level programming language, which is called this great name, planned calculation. Beautiful thing. But he's the first person to suggest a universe built around computation. Which is now a theory that's very hot in physics, that the universe is nothing more than mathematics and computation. And the name of the paper he wrote this in is called Rechnender Raum, Calculating Space, 1969. So he was 30 or 40 years into his time, and he was also a pretty decent painter. I don't know, Rachel, you're the expert here, but I actually like his paintings are really cool. They look a little bit like what you call science fiction art now, but again, he was doing this 30, well, I guess this was the 50s, so 20 or 30 years before they did this, and there these very vivid colors, strange geometries, and he was generally, an interesting guy who's basically not known. So you can say, when people ask you who invented the first programmable computer, you can be Konrad Zuse. So now we're getting to yet another person who, as I said, the reason I'm doing the hardware world is this is littered with brilliant, interesting people, whereas the software world is kind of littered with dull, regular people. And this guy, John von Neumann, is is described often as a super polymath. This guy worked in mathematics, physics, economics, game theory, cellular automata. He was the guy behind the Manhattan Project, which he somewhat regretted afterwards, but as he said, at the time, at the time we really did not want Hitler to get the bomb. And he paid a pretty bad price for this because he died of cancer not very long, 57, not very long after the war, almost certainly because of his ongoing involvement with radioactives. So it's really, and he invented, it's not just that he did all these things, like the game theory, he invented game theory. Cellular automata, he invented cellular automata. He did all sorts of things in physics. He probably would have gotten the Nobel Prize if he'd lived. He was just an amazing guy, and also very funny and witty, and an atheist. And when he discovered he had cancer, apparently he really understood the consequences. He was not looking forward to personal extinction, and all the people around him were very grim for the last year of his life. Sorry. So that's kind of the sad part of this guy. And he was very, very influential in computing. And particularly, he was the first person to talk about the stored program computer. We're finally getting this stuff you may use. All these other computers we've talked about may have been programmable, but they were programmable by rewiring the computer. You'd be programming these with a screwdriver. Now, you're not going to get very far with this. He was the first person to say, maybe the storage mechanism can also hold the program. That's again, you kind of it's one of those things that has to sink in that it's a big insight. Today, oh yes, the program's stored on the computer, I can change it, I can load another program from the internet. Right? No big deal. But he was the first person to conceive of being able to load and store and save programs. Before then, they expected to rewire your computer for each thing. And particularly he has this thing, he came up with what's called the von Neumann architecture. And this, I'm not going to go into this deeply here, except to notice that most programs, most computers are done either with this or the next one, the Harvard architecture, which are very similar. The key thing that you're going to vaguely need to remember in this, computers are so fast for what we're going to be doing for this, it's not even going to be a huge problem, but the closer you get to the center, the faster everything is here. This is a central processing unit. These days it's a tiny little chip. Back in the day it was a room, but whatever it is. Everything moving around here is really fast. Here's your big memory store. Getting to here is pretty fast, but these arrows are maybe 10 to 100 times slower than moving in here. These are your input and output devices, your keyboard, perhaps your mouse, your hard drive. Again, another factor of 10 to 100 slowness. So if you do calculations going in and out of here, when you want to be in here, it could be 10,000 times slower. 10,000 times. Of course, everything's really fast today, but it's just, I don't expect you to memorize this thing. What I do expect you to remember is that whole thing that the more stuff we can do towards the center, the better. The Harvard architecture has it much closer there. There they even, skip it. It's not even that exciting. So now we're getting to the age of dinosaurs. Big lumbering things. What do we have? We have huge unreliable computers. And in fact, ENIAC in 1947 was basically based on John von Neumann's work. It was originally intended for gunnery. Yes, it's the military again. And they turned it on in July 29th, 1947. It operated continuously for 8 years. But it's not so, all is not rosy. It was huge. 17,486 vacuum tubes, these little things like this is. 7,200 crystal diodes, and an astonishing 5 million solder joints, all done by hand. All done by hand. And this was done by some of the best people in the world, so they actually had very few troubles with solder joints. Oh, and I should point out it was 8 feet by 3 feet by 100 feet long. So, I mean, this picture doesn't give you, this is only a part of the whole thing. It's actually a vast, great room full of these machines. And the trouble with this is, multiple failures every day of the machine. Basically, and it wasn't even, they very quickly found the very few solder joints. They did a very, very good job building this. People were very dedicated to this. But vacuum tubes only have a limited lifespan, and when you have 17,000 of them in your machine, they were initially having 3 or 4 failures a day. Well, so later on in 1948, they got these long life, very expensive vacuum tubes. So then they only had 1 failure every 2 days. But that's still, the trouble is that doesn't get any better as you build a good big computer. It gets worse. If you tried to build a computer 10 times as big, you'd be having 5 failures a day, 10 failures a day on this sort of thing. 5 failures a day, and that's using the incredibly expensive vacuum tubes. So people were just stuck. They were kind of like, well, this is as big as computing can ever get, because we have this problem where literally people were walking around with shopping, and when they first started, they had like supermarket shopping carts that they had stolen, filled with vacuum tubes that boys would run around with things. So it wasn't, they were like, okay, that was the end. That was the point where, around this time, somebody at IBM said, in the whole world, I believe there's a market for perhaps 6 computers. So how did we get out? So here we are, we have these huge behemoth rocks that couldn't possibly work into integrated circuit. I like this picture because it's on the stem here. And you can see, what you do now is you print multiple circuits. You print is the key word onto one tiny chip of silicon. That's why it's called a chip, because you can cut a chip off silicon. So, and it's printed with a lithographic technique, which used to be optical, and now they use electron beams. So very exciting. But what it is, it's like photography. It's done with photography. So you actually, or light photography. So you can think of actually printing a photograph of the chip onto the chip itself. So instead of having to build this, you actually just take a photograph and project it so there's no moving parts and there is nothing to go wrong. Occasionally, it's true that occasionally the chips get misprinted. Even these things get so small, you'll see in a few seconds, that even a tiny particle of dust can completely blow it. That's why you see all these people dressed up in these, I should have had a picture, but clean rooms, everything's white, and they're wearing gloves and all this sort of stuff, because one particle of dust can destroy this, but you discover that right away. Once it's going, it'll last for perhaps 50 years without any problems. So this great thing called Moore's Law, astonishing enough, this guy, his first name, Moore invented this in the 60s, and he said that the number of circuits you can get on a chip will double every 2 years. Nobody has any idea how he guessed this, but it turned out to be, and something where something keeps doubling in the real world, that just doesn't happen. When population keeps doubling, well, your petri dish runs out and they all die, Human population keeps doubling. At some point we're gonna, maybe 10 billion, maybe 20 billion, but at some point we're either gonna stop reproducing or it's gonna be bad. But this has kept going since he originally proposed it. I hope I put when it was, Gordon Moore, God. Predicted 1965, and in fact we've kept that pace up pretty well to the present day, doubling every 2 years. And the reason I'm really including this, I said one day it's got to run out, but they keep going, keep confounding things. The reason I included this specific thing is mainly because the graphics are really spectacular. Here's where we go. So we start off, this is the absolute first transistor. This is one transistor in 1958, and this is actually magnifying glass size. It's probably about the size of my thumb. There's one circuit in that thing, and they made this by hand in 1958. So in 1959, we have two transistors, and this is now what's called planar. This is the first time they actually did the photographic technique I mentioned before. So 59, there's two transistors. Now 61, you see it's doubling. 4 transistors, still not very much. But then we go to the 60s, this has got 32 transistors already, still not so impressive. So now we get to 1974, this is the 80, this is 5,000 transistors, the first programmable home computer, the Altair ran on this one. Okay, 5,000, it's pretty impressive. You can see that they filled in everywhere they had, you see everywhere had space before, they're filling in details. Okay, well that's quite impressive. So in 1978, we get to the 8086, it's a shame these pictures aren't coming out, but you can see that there's still some detail in there, but everything is being grossly filled in. Now we get to some of the more visually beautiful pictures. This has got 275,000 transistors, and now you see these weird colors appearing, and you'll see them even more. That's because the size of the features is less than the wavelength of light, or comparable to the wavelength of light. After this, it was about this, there were probably 3 wavelengths, but that's why you see these beautiful interference patterns on there. So, and we're starting to see things where you, even zoomed in, you couldn't see any detail. Like this is just a big chunk of memory in there. And again, it keeps going. We get this one here. All these pictures aren't as beautiful. I want the Pentium is, 3.1 million transistors. And we get the Pentium 2, 42 million transistors. It's astonishing, ridiculous amount. There, this is where you start to see the rainbows actually occurring in this. Then we get 2007, this is a Core Duo, 410 million transistors, more than one for every person in the United States. And at this point, they were running out of ways to organize them. They're like, oh, okay, we're going to now take 2 of these chips, 2 of these processors, and we put them on one chip. So you can see this thing is actually symmetrical there. This is half of it, and this is half of it. There's actually 2 independent brains working in here. And then the finally one, we have a more or less current one from 2009 that's called the Phenom, which I love this. And it's 758 million. That's almost 1 billion transistors printed on this thing. And this one's actually, is there one more over here? No, there is not. And this one is actually a quad-core machine. It's actually 4 separate computers on this tiny little chip, about the size of your thumbnail. There are limits. Like these things are so hot that about now the actual those white spots, if they weren't, they're like a lot hotter than the surface of your stove. Much, much hotter. Getting towards the heat that you would get towards the surface of the sun, which isn't outrageously hot. Actually, the sun gets really hot in the center, but the surface isn't that hot because it's kind of wispy. Still, they get incredibly, incredibly hot, and it's becoming a big problem. Like you notice now in your machine, you have this, you can't even see the chip because it's surrounded by this huge block of radiating material. It's welded into aluminum to let all this heat radiate out, mainly because you have 758 million little tiny things, each one giving off heat. So there's a work rule there, which is never touch the chip on you. I did it once. It'll hurt. It's literally like touching the stove, only worse. So don't do it. You can't do it anymore, as I said, because of lots of these things. All right, on the software. I'm going to go through this pretty quickly, but there's some terms you need to know. So remember, we had the idea of the stored program computer, where the memory, the program is contained in the memory. It's not done through wiring, it's contained in the memory. So the language of the machine is lots of tiny little numbers. You can see here what it looks like. Isn't that clear? No, it isn't clear. When people were first doing it, they discovered it's hard to write, it's hard to read, and it's hard to fix. There's a classic story, I didn't include it, but I've got to tell you this. Early day, first computer in England, one of the first computers, this mathematician was hired to write programs. I mean, they didn't even have the term writing programs for computers, but he was. And so he says, oh, I have to write a square root algorithm, that's what I'm going to do this. So he writes it, he's like, well, great, that was fun, what am I going to do in the afternoon? He's like, oh, I just think I'm going to try out. Let me try it out and see if it works. So he plugs in a number into it, and to his shock, it doesn't give him the square root. And he's like, that's bizarre. So he's like, he goes and he's like, oh, I made an obvious mistake. So he fixes that obvious mistake and he runs it again. Again, it does not give him the proper square root, to his shock. And then he had this sudden realization that a great deal of the rest of his professional life was going to be discovering bugs in programs he had written. And the charming part is that he actually sat down and wrote it, and he didn't even think that, he just assumed it would work right the first time. And of course, now we know that's just not going to happen. Okay, so assembly language, well, what's that? And we have, well, it's basically like machine language, but in words. And you can see, look, you do something, you load, oh, it's not so good. It's basically these tiny little instructions that say, move this number to here, add this one number to this, move it to here. I program in this, don't do it. You don't want to do it. It has the same problems. It's hard to write, hard to read, and hard to fix. So now we go to what are called high-level languages. You can see we're getting finally to something you may care about, or it may find useful to you. High-level languages. You express your ideas in a high-level way. The computer does the hard work of the translation, and you can choose, I couldn't get that last thing not to there. And you choose between compilers and interpreters. I'll explain what those are. Easy. Well, not necessarily so easy, but you know, it's a lot easier than doing it in assembly language. Very quickly, I'm going to go through this. Compilers just translate a high-level language into machine language. And you get a really great results, but it's a lot more work, because you have to, every time you make a change, you have to go through this whole compilation process. In some cases, it can take several minutes. Really annoying. Interpreters, basically, is interpret the human readable language as you go. So that you tell it what to do and it interprets it. The advantage is immediate feedback, introspection. You can actually look at the code, can look at itself because it's done this way. The downside is it's a lot slower and a lot more memory. However, we're going to use Python, which is interpreted language. So here's some I'm just have a little list to show you how many languages are. I have these are languages I've written programs in at various times. The yellow ones are interpreted and the green ones are the yellow ones are compiled and green ones interpreted. So you can see that there's rather a lot of languages. Oh, I had PHP twice and I hate it too, so that's terrible. These are all languages I've been programming at some point, and there's too many languages. Now, I said I wasn't going to say too much, but I have to talk about Grace Hopper. Very, very cool individual. Basically, the Navy decided they wanted to do computers. So they had 3 committees. They had a long range, a medium range, and a short range committee. The long range committee never met. The medium range committee met, but by the time they had, Grace Hopper had already invented the first compiled computer programming language called COBOL. And it's kind of a rip-off for her. She was not well treated because she was a woman. She actually had a PhD in mathematics before she joined the Navy during the war for patriotic reasons. And then she tried to stay on and go on the Navy, and they would not transfer her, partly because of her age, partly because she was a woman. She invented the first language, the famous COBOL, which back in the day we used to make fun of it terribly, but it actually turns out not to be a bad language. And also, she has another thing she's famous for, I want to bring up. She found the first bug. Here it is. They had a problem with the thing, they had a problem because it failed, and relay number 70 panel, moth in relay, and they taped the moth into the book. And then she actually wrote, this is her handwriting, saying, first actual case of bug being found. Now, the term bug had actually existed, I thought that was where it came from. When I looked up, bug had actually existed for years. So, but still, very funny, so I had to include this. All right, finally, Python, invented by Guido van Rossum, who single-handedly brought back the name Guido for me as a serious name here. And it's just really his life's work. He started in '89, blah, blah. He's been steadily working on it. We're up now to version 3, which we will not be using. Version 2, the differences aren't so great. Really the great thing that happened in there is he became the BDFL. BDFL, yes. In 1995, he was named Benevolent Dictator for Life of Python. It's a really great system because it's a community-run thing, but they argue and argue, and computer people argue much more than people at Silent Point, let me tell you. I don't think he ever really believes it, right? So people argue there, and then eventually he comes and he's a very nice guy and very rational. He says, okay, we're going to do this. And he's a little conservative, as he has every right to be, but he's very open to things. He's very open to reasoning. Everybody loves it, even people get overruled. So that's him looking very benevolent and dictatorship. This sort of thing is. So why Python, blah blah. I think I've already told you. It's easy, easy. That's the number one reason. Easy to get started. It's really clean. It's really slick. You look like you can. It looks like it doesn't even look like English. It looks very clean and easy to read. And it's got great list processing, great string processing, which is essential for all you poets out there in the audience. And it's a huge selection of libraries to do everything. Anything you wanted, there's probably a library in the thing already, or you can get a library. So it's just like it's like a marvelous Swiss Army knife. And a big deal is it's free and it's open source. Nobody can ever charge you for Python. You can just download it. If there's something you don't like, you can change it. Okay, we're going to take a 5-minute break here. There's people drinking, and this sort of thing is, as I predicted, we're running a little bit off. What time is it, by the way, actually?
1:19.
Oh boy. Well, that's very impressive. I actually hit my mark. I'm only 5 minutes late. So take a nice 5 minutes, and then we'll come back with the inspirational part. Thanks a lot.